Hello there, my name is David Liu, and I will be presenting on the second lab of Introductory Physics 1 at Georgia Tech titled Motion of a Falling Object. The purpose of this lab was to capture the video of a motion of a falling object and compare our observations of it to a computational model. We factored drag in one model and then disregarded it in another. Our system in this experiment encompasses the object, or a dry eraser in our experiment, and the surroundings encompass the remainder of the lab, such as the lab floor and the meter stick. The main physics ideas here included the velocity update formula, the position update formula, and line graphs that depicted these changes over time in accordance with Newton's second law of motion. The force of air resistance, also known as drag, must play a role in this experiment. The weight vector, or weight force, is equivalent to the mass of times gravity times the negative y hat vector, or j hat, when positive y is pointing upwards. This is because the direction of the vector is downwards towards the Earth's surface. It exhibits a proportional relationship, meaning that a constant can be substituted and multiplied by the object's mass. The constant b, which reflects the object's properties such as its shape or size, must have the units of newtons times seconds over meters due to dimensional analysis. We dropped the Staples dry erase board marker for our physical model from a height of approximately 1 meter. The video was analyzed using the computational tool tracker, for which the model eventually relied upon. Our model's predictions substituted values determined from the initial or previous slides, and the initial position and velocity assumed to be 0 or around 0. Moreover, the time of each step was considered as well. In accordance with the 30 frames per second, it was approximately 1/30 of a second for our time step. The previous formulas and physical principles were eventually translated into code, as shown on the next slide. Here, as it was iterative, we showed that t was added on to delta t, and thus updated as the code ran through each line. Here, in accordance with the physical principles and the glow script links found here. The results were displayed here. The predicted initial velocity was derived from the first 2 points extracted from the tracker tables, in which the coordinates of the starting position and elapsed time are 1/30th of a second, corresponding to a video with a frame rate of 30 frames per second, as stated previously. The initial velocity was assumed to be non-constant, and then equal or approximated to the final velocity as the average velocity. The final time corresponded to roughly 0.567 seconds in, and the mass of the eraser was roughly 4.5 hundredths of a kilogram. In this instance, there was a non-zero net force. A crucial physical model was that our net force could be modeled by negative b times v squared minus mg, or alternatively the drag coefficient b factored in. Our computational model showed that drag, when it was factored in, would have the eraser hitting the ground at an earlier time than when it was simply just gravity. Both of our computational models showed that there was actually less time elapsed between the eraser hitting the final position than was observed. There were many different types of error that may have been present in this experiment as well, such as environmental or confounding factors from the uncontrolled environment, and systematic and instrumental errors due to the high-speed clicking and insufficient frame rate as previously seen in Lab 1, rounding in the spreadsheet insignificant figures, as well as blunders, namely the inability to drop the eraser in a straight line. These results provided conclusive findings. The model deviated from the actual position gradually after about 0.2 seconds. A terminal velocity, in answering the what if, was that it was reached when the drag had balanced the force of gravity, or when there was no net force acting upon the eraser. Our hypothesis was that an object would reach the same terminal velocity regardless if it was thrown down. However, it would take less time for the object to do so, and as depicted by the computational model, would depict at a roughly non-zero y-intercept. In short, these data have demonstrated that there may be slight differences between what is predicted and observed. This divergence can be accounted for in the differences between these conditions. Thank you for watching.